Okay, so just remind yourself for the moment what asymptotic density is. So the asymptotic density of x, denoted by rho of x, is the limit as n goes to infinity of the number of ones in the first n bits of x divided by n. So classic example, the asymptotic density of the evens is 1/2. Just a minor note, if you have an overline over that, that's the upper density, and an underline is lower density, and that's the lim sup and the lim nth respectively. Okay, so then intrinsic density is asymptotic density that's invariant under computable permutations. So you have the asymptotic density of pi of a is the same for every computable permutation pi. We say a set is intrinsically small if it has intrinsic density 0. And we denote intrinsic density by capital P. Once again, the overline and underline are the lim inf or the lim sup and the lim inf respectively. This time that limit is over permutations. Okay, so sort of the original motivation for this project, the initial question that we set out to answer, what values in the unit interval can you achieve as the intrinsic density of some set? And the short answer is, well, everything, and it's not too hard. As pointed out by Laurent Bienvenu, you simply do a probability theory argument. You don't really need to get into computability theory at all. And you see that, you know, measure 1 with respect to the R Bernoulli measure, mu R measure 1 of those sets have intrinsic density R. What is the Bernoulli measure? Just a reminder, it's the biased coin flip measure. So if we have some fixed number R in the unit interval, we say with probability R, I'm going to get a heads when I flip this coin, and with probability 1 minus R, I get a tail. So this question isn't interesting on the surface, but as we're going to justify in a little bit, there's still some things to pick at here. So let's get into that. So a finer motivation is, how can we understand sets of different intrinsic densities in relation to one another? And one reason we might want to ask this question is because if you look at things, it becomes very obvious pretty quickly that full mu R randomness is a fundamentally different property as a class than intrinsic density. One of the great examples is if you have two sets of the same intrinsic density and you join them together, then the resulting set has intrinsic density the same as those two sets. Clearly, this is not true for random sets. If you join two random sets, that's no longer random. So what we're going to do is we're going to pick at this question a little bit and see, just sticking at the level of intrinsic density, how can we study how these sets interact? How do sets with different intrinsic densities interact with one another? And so on and so forth. And the question you might ask is, what are you going to use to do that? And we're going to justify why in the title of the talk we say non-computable coding methods, because coding methods that are fundamentally computable, they're very unsatisfactory for this goal here. So just to reiterate that general idea, we want to find, our goal is to find some method of combining two sets A and B such that the output of that combining process gives us a new set whose intrinsic density is a function of the intrinsic densities of A and B, ideally some interesting function. And the into operation, which is going to be our main tool for this talk, our first non-computable coding operation, it's going to do this nicely. But before we get into that, let's just see why a more obvious choice of function doesn't work for our purposes. And to do that, well, if we're computability theorists, the first thing we think about when we think about combining two sets in computability theory is the joint. And the theorem that if you have, I mentioned this a little earlier, if you have the joint of two sets, then that has intrinsic density alpha, if and only if both of those sets have intrinsic density alpha. For one direction, it's not too hard to prove. If they have different intrinsic densities, then you can find permutations that make them look different. They have different densities, so you can cook up permutations that do essentially the same thing on the joint for each half. So those two different permutations would make A join B have different densities, so it couldn't have intrinsic density. The other direction is a little harder, but it's just essentially writing some things down, doing some analysis, and checking the details. Another candidate that you might think of is the Cartesian product, but things are even worse than the Cartesian product setting. You can't even hope that the Cartesian product will have asymptotic density in general, and you can do some things to ensure that happens, but you still, no matter what you do, you won't be able to fix it for intrinsic density. And it comes down to, it depends on the pairing function that you pick, and that's why intrinsic density is a problem there. Okay, so that's the motivation for why we're not going to use computable coding methods, and we're going to look at some non-computable coding methods. So our first one, sort of the protagonist of the talk, so to speak, is the into operation. So we're given two sets A and B. Throughout the talk, we're going to represent them as increasing elements. So A sub I is the ith element of A, and B sub I is the ith element of B. If we have these two sets, then B into A is defined by A sub B0, which is less than A sub B1, which is less than A sub B2, and so on and so forth. So we just take A, and we think about it as our new universe. Our old universe was omega, and we look at A as our new universe, so we just enumerate the elements of B along A like we would in omega, but now we have some gaps given by A. So let's look at some examples of this operation, see how it works. If E is the set of evens, then E into E is what you might expect it to be. It's the set of multiples of 4. The nth element of E is 2n. So E into E is the set of E sub n, which is E sub 2n, or 2 times 2n, which is 4n. Similarly, if O is the set of odds, then E into O is the set of naturals congruent to 1 mod 4. And it's similar argument. You just unpack the definition, it falls out. So more interestingly, for any two sets A and B, A join B is the disjoint union of A into E union B into O. Okay, so some basic properties of the into operation. A into omega is A. Omega into A is A. B into A is always a subset of A. And that's why, if we go back to the previous slide, we have the disjoint union here. A join B is the disjoint union of A into E and B into O. Because A into E is a subset of E and B into O is a subset of O, that ensures the union is disjoint. And sort of more generally, expounding upon that, B into A, disjoint union, the complement of B into A, that's all of A. Why? Because each index is either in B or it's in its complement. So each element of A is either in B into A or it's in the complement within A, which is B into A, B complement into A. And the into operation is associative. Okay, so our main goal in this talk is going to be to talk about density, but I just want to sort of justify why we're calling this a coding method and why we say it's non-computable. So in general, if I take A into B, if I just have A into B, I can't necessarily recover A or B. But unlike, say, the intersection or union, I actually only need one of those sets. And we're going to see that in this application. So we have a little lemma here. If I have some class of sets, some subset of 2 to the omega, and it's closed under subsets, and it's closed under self-join, which is to say I have some element X of this, which has this property, then X join X also has this property. If both of those conditions hold, then the P degrees are closed upwards. What's the proof? Well, if we have A, which computes B, and B is a P set, then B join B is a P set because it's closed under self-join. B join A into B is a P set because it's a subset of B join B, but A is Turing equivalent to B join A into B because A is the set of n, where both 2n and 2n plus 1 are in this set, B join A into B. Okay, so that's the proof. And one nice little application of this lemma is that the classical result due to Martin and Miller, that the hypermune degrees are closed upwards. It's not hard to check that hypermune degrees, or hypermune sets rather, have this property here, or both of these properties. Okay, so that's a cute little lemma. But this, this result that we obtained as a corollary has a bunch of different proofs. So why should we necessarily care about this? Well, we can actually use this lemma to prove something new that wasn't known before, but that requires a little background. So Eric Astor showed that the degrees of intrinsically small sets are exactly the higher DNC degrees. And to do this, the proof relied on Karl's result that the degrees of any collection, which is closed under subsets and has an arithmetical element, are closed upwards. So if you try and relativize this and think about the X intrinsically small sets, that is the sets which have density 0 under every X computable permutation, almost all of this proof relativizes just fine. But Karl's result has a little sticking point because there are some sets that have no arithmetical intrinsically small set. The canonical example is the omega-th jump. But fortunately, in this setting, we can just replace Karl's result with the lemma we just proved to show that this relativizes in general. So it really is the case that the X high or X DNC degrees are the degrees of X intrinsically small sets. And it's worth noting that this isn't, a refinement of Karl's result because it doesn't apply to the cohesive sets, which was the original motivation for his upward closure property. So it's just a different principle that can apply in different scenarios. Okay, so that's a little motivation for why we call this a coding principle. Fundamentally, if we have, the universe set, then we can recover the into set in some sense. We don't need both sets like we would need with the union or the intersection in general. Okay, so let's turn to talking about into and how it applies to asymptotic density. We have a lemma here. It says if I look at the upper density of B into A, it's less than or equal to the product of the upper densities of A and B. And similarly for the lower density, but it's greater than or equal to in that case. The proof is just simply, teasing at the definition of what is the upper density and how does it operate for sets. And the one thing you'll see is that sort of a subsequence of the finite densities of each stage is the densities where the last bit is a 1, and that subsequence dominates the original sequence. And from there, you do some algebra and you tease out this inequality. But the important corollary is that if both A and B have defined density, if their upper density is equal to their lower density, then the into operation multiplies asymptotic density. And that's going to be sort of the running theme is that each different notion of density we'll look at, under some assumptions, we're going to be able to recover this result that the into operation multiplies densities. So it's a nice tool for combining two sets of given densities, no matter what your notion of density is, and creating some set of potentially new density. So as I said, this is true for intrinsic density as well. So if you have A has intrinsic density alpha and B has intrinsic density beta relative to A, then B into A has intrinsic density alpha times beta. And this is sort of our core theorem that gets us to most of the results that we want to get, at least in regards to intrinsic density. So one question you might ask yourself before we talk about how the proof goes, is this best possible? So in the asymptotic density case, we just said, if I have two sets A and B and I have density, then B into A has density alpha beta, boom, 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 it all works out. Here for intrinsic density, we have this extra relativization that B needs to have intrinsic density relative to A. So the question is, can you get rid of that? The answer is no. You can't get rid of the fact that A needs to have intrinsic density. The example is obvious, just omega into A will show that A has to have intrinsic density. For B, if you take any set of intrinsic density 1/2 and look at it into it join its complement, then that will equal it join the empty set, which can't have intrinsic density because it's a subset of a computable set. Okay, so that verifies that at least in general, this is best possible for this theorem. In order to prove this theorem, we actually need to introduce our other non-computable coding operation. So let's see what that is. The within operation is a natural dual to the into operation. So once again, we're given two sets, and we define B within A to be the set of n such that the nth element of A is in B. And this definition might seem to come out of nowhere, but here's the idea behind it. B intersect A is a subset of A. Therefore, there must be some x that we can apply the into operation to end up with B intersect A. So the within is just giving us that x. So it's the set x such that x into A is equal to B intersect A. Okay, so let's look at some examples of how this works and get a better feel for the operation. If T is the set of multiples of 3, then T within E is T back again. So if we look at T within E, by definition, that's the set of n such that the nth element of E is in T, or the set of n such that 2n is in T. Well, that's the set of n such that 6 divides 2n. Well, 6 divides 2n if and only if 3 divides n. So it's T once more. Conversely, or differently, T within the odds is the set of naturals congruent to 1 mod 3. And sort of follow through a similar argument, you'll see that this is the set of n such that 2n plus 1 is in T, which tells us that 2n has to be equivalent to 2 mod 3, or n has to be equivalent to 1 mod 3. Okay, so that's sort of how it works. What are its properties? Well, omega is A within A. That's sort of straightforward because what indices of elements of A are in A? All of them, so omega. B within A, disjoint union B complement within A is omega, sort of for the same reasoning as before. If B is a subset of A, then B within A is the set X such that X into A gives us B intersect A, but in this case, B intersect A is B, so B within A into A is B again. Within is not associative. There's an example here. It's not terribly enlightening. It's just sort of check the definitions, play with some numbers, and you'll see that the order can matter depending on what sets you're looking at. Okay, so going back to intrinsic density, we have a lemma here. If C is a computable set and A has intrinsic density alpha, then A within C has intrinsic density alpha as well. And if you think about it, this makes sense because what this is saying is, if I take some set of intrinsic density and I only care about it on a specific computable set, I don't care what it does outside this set, well, it should still have intrinsic density alpha along this computable set because there's a permutation that makes this computable set look like everything. And then you can apply a permutation from there and it should still look like everything. And the proof essentially goes along that motivation. You just have to keep track of the details and do a little bit of baby analysis. But this motivates how we're going to prove our central theorem, which is what we're ready to do now. So just a reminder of what that theorem said. If A has intrinsic density alpha and B has intrinsic density beta relative to A, then B into A has intrinsic density alpha beta. And the proof sort of goes as follows. We have some computable permutation pi, and we want to show that pi of B into A has density alpha beta. Well, we know that pi of A has density alpha. So if we can show that pi of B into A within pi of A has density beta, we can apply our result about asymptotic density and we'll be done because it will multiply the asymptotic densities. So to prove that, we just construct a computable permutation pi sub A such that the density of pi sub A of B is equal to the density of pi of B into A within pi of A. So that will have density beta, and we'll apply our asymptotic density lemma to get density alpha times beta. Boom. And obviously, there's some details involved in constructing this pi sub A, but that's the general sketch. Okay, so let's see some applications of this theorem now. As a corollary, if you have the same requirements on A and B, then their intersection has intrinsic density alpha beta. What's the proof? Well, we just apply our lemma, or our theorem about into and our theorem about within. The intrinsic density of A intersect B, well, that's the intrinsic density of B within A into A, because those are the same set. B within A has intrinsic density beta relative to A by the relativized form of our within theorem, so we can apply our into theorem to multiply the densities. Okay. The union is, we sort of already know from the outset that under certain requirements, infinite unions for intrinsic density sum up intrinsic density as you'd want them to. The issue that you have to watch out for is that you can't have countably many, say, finite sets and combine them to get an infinite set. So you have to have that the tail of your union has absolute upper density 0, but that's just a technical concern. As long as things are nice enough, infinite unions work just fine. And this essentially follows from Jokic and Shoup proved this for regular asymptotic density, and it just falls out pretty much immediately for intrinsic density. Okay. So now we have this lemma that says I have a countable disjoint sequence of sets, A sub I, such that each A sub I has intrinsic density 1 over 2 to the I plus 1, and the tail goes to 0. And having seen this lemma, you can already guess sort of the direction this is going, given that I've already told you infinite unions sum up densities. So first, let's just quickly look at the proof sketch. If X is some one random, by the general form of Van Lambergen's theorem, the columns of X give us countably many one random sets relative to one another. By the fact that one randomness is sufficient to get us intrinsic density, this gives us countably many sets of intrinsic density 1/2 relative to each other. So we can just do the following process. We start with omega, and we put the first column of X into omega, and we put its complement into omega. So this gives us 2 disjoint sets, each of intrinsic density 1/2. So then we pick one and we set it aside. That's our first set AI. We take the other one and we split it in half again using the next column of X. And we just keep repeating this process. This gives us disjoint sets with the right intrinsic density. If you just check the randomness that you get from Van Lambergen's theorem will ensure that everything is met for our into theorem to work. Okay, so once we have that now, we have this corollary that if you have some element of the unit interval, then with that number R and any arbitrary one random X, you can compute a set of intrinsic density R. So all you do is you take this set of ones in the binary expansion of R, and you add up the AIs that we just defined along that set, and that has to have intrinsic density R. So a little corollary of this is that if R computes a one random, then R computes a set of intrinsic density R. Why is this important? Well, there's a result of Kjos-Hansen that every mu R, one random set, computes R. In particular, R can't compute any mu R one random sets. So this corollary tells us that in the case of R computing a random, this gives us a different example of intrinsic density R than the mu R random that we talked about at the beginning of the talk. So this is giving us more things, which we sort of knew should exist because, for example, intrinsic density is preserved by Jones, which randoms are not. Okay, so that's sort of the end goal of what we set out to do with intrinsic density. So now we're going to shift gears and talk about the last concept in my title, which is stochasticity. So the idea of stochasticity is that we have a list of countably many 0-1 valued coins that have been flipped, and we can see them laying out in front of us. We're identifying the sequence here with a set, the set of n such that the nth coin is a 1. So what we want to try and do, and we might not be able to do, is we want to look at this sequence of coins and somehow select from it a subsequence that has a different ratio of 1s to 0s as the original sequence. So say our original sequence is 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. If we select the even coins, that gives us a subsequence of density 1. The original sequence had density 1/2. So we've successfully selected a sequence of different density than the original subsequence. A set is stochastic if we're not able to do this. So in some sense, the sequence is sufficiently foreign to us that we don't know enough about it to select a subsequence of different density. Of course, what stochastic means depends on how we're allowed to select coins, because if you're allowed to select coins in any way you want, you can just select the ones that are 1 or select the ones that are 0. So we're going to have limited selection rules that make this a meaningful notion. So we're going to start with injection stochasticity, and then we're going to see why we care about this at all. So formally, X is R injection stochastic if the asymptotic density of I inverse of X, or the set of n such that I of n is an X, if that has asymptotic density R for all total computable injections I. So how we're thinking about this is that we're given some sequence of coin flips X, and we're unable to select a subsequence sort of independently of what X does, just by saying, I'm going to take the 17th coin, then I'm going to take the 3rd coin, then I'm going to take the 15th coin. We're unable to change the density doing that. For those who are familiar with randomness in some sense, injection stochasticity is the uniform version of KL stochasticity. So it's independent of your input set in some sense. So let's just see sort of an illustration of what's going on here. So we start with our sequence X on top, and that's some 0s and 1s. And then we're given some total computable injection I, and we look at I inverse of n. And you see some places, some things aren't in the range of I. So those coins we completely ignore. Things that are in the range of I, well, they got sent there by some number in the domain. They're equal to I of n for some n. So we take I of n and we map it back to n. So we start here and we say, okay, 0 went to 4. So we take the 4th coin in X and we move it to the first coin in our subsequence Y that we're trying to build. Okay, 1 went to 1, so the first coin stays as the first coin. 2 went to 0, so we take the 0th coin of X, and that's the 2 coin of Y. And we just continue in this fashion. And some coins are missed, but what we do have is, we eventually get a full sequence for Y, and then we just look at the density of this. And in this case, it's relatively similar to the density of X. Okay, so why do we care? What does this have to do, anything whatsoever, with what we've done so far? Well, Astor proved that your R injection stochastic if and only if you have intrinsic density R. So there's a connection right there. By studying the intrinsic density R sets, we've sort of stumbled our way into studying things that we care about from an algorithmic randomness perspective, which is stochasticity. Okay, so I'll get our general overview of motivation in a bit, but that's sort of why we're going to look at other notions of stochasticity from the literature and talk about them using the tools we've developed so far to talk about intrinsic density or injection stochasticity. So another sort of famous notion of stochasticity that you'll find in the literature is church stochasticity. And here the idea is we've taken our sequence of coins and we've covered them up by cups. So we can't see what the values of the coins are. So the first thing we have to do is we want to decide whether or not we want the first coin in our subsequence. With no information, we just decide to take it or leave it. Once we make that decision, we look under the cup and see what it is. And then we can't change our decision knowing that value, our decision stands. But now we can say, okay, I've seen a 1. The first coin is a 1. And I didn't take it because I didn't have any reason to. I didn't know anything about my sequence. Now I'm going to take the next coin. I don't know what the next coin is, but I do know what the first coin is. So I take the second coin, add it to my sequence, then I check the value. And I continue in this manner. So to decide if I want to add the n plus first coin, I am allowed to use information about the first n coins. So if in the first 8 coins I see 1, 0, 1, 0, 1, 0, 1, 0, I might say, okay, I think the next one's going to be 1 because I see a pattern developing here. Okay, so that's the idea for church stochasticity. Formally, what this represents, we have some total function f from finite binary strings to 0, 1, which represents how we select coins. And this induces a map on Cantor space defined via f hat of x is the set of n, such that the first n bits of x are selected by f. So what that's saying is f looks at the first n bits of x and says, okay, I want to select the next coin based on this information. We're going to abuse a notation and let f of x be the same as f hat of x. Okay, so x is R church stochastic if for all such selection functions, either the number of things selected is finite or the density of x within f of x is R. Why do we care about this? Well, if you recall the definition of the within operation, x within f of x is the set of n such that the nth element of f of x is an x. In other words, x within f of x is sort of eliminating the coins we didn't select and then collapsing them into a sequence. This is just using our notation to represent that idea, and we're measuring the density of that. Okay, so let's look at sort of a picture of what's going on here with church stochasticity, just to get a better feel for it. So we start and we have just blank spaces here. All the coins are under cups, so we don't know what they are. So this represents f of the empty string. And it's saying this pink circle here, I have no information, so I don't want to take it. I didn't select this first coin of x. So now we look under the cup and we see that, okay, the first coin was 1 valued. And now using that information, we say, okay, maybe x is all ones, who knows? So let's select the next coin. And that's what the blue circle represents here. So at this stage, we've used the fact that our first bit was 1 to select the second bit, but we don't know what the second bit is. Okay, so we look under the cup and it's a 0, which isn't necessarily ideal. We thought it might have been a 1. Okay, so now we say, I have no idea what's going on, so let's just select the next bit for giggles. So we have a blue circle once again, we've selected it, and here the information we're using is the fact that the first 2 bits were 1, 0. So that's f of 1, 0. Okay, so we look under the cup and it's a 1. Hooray, that's sort of what we wanted to get. So now we say, okay, I had a 1, then I had a 0, then I had a 1. So maybe this is alternating, 1, 0, 1, 0, 1, 0, 1, 0. That's our new hypothesis. So we're not going to select the next bit because we think it's going to be a 0. And we've made this decision using the first 3 bits. Okay, so it was a 0. And now we're operating under the assumption, in some sense, that we're going to get 1, 0, 1, 0, 1, 0. So we want to select the next bit. And okay, so our hypothesis wasn't correct. We see a 0 again. So we don't necessarily know what's going on there. But so far, we've added 3 things to our subsequence, and we can't go back and change that. Once we've made a decision, we just have to commit to it. So we say, okay, the next bit, I'm not going to select it because, you know, what I thought was going on is completely out the window. So let's continue. Okay, and this goes on to infinity, or for all n. So f of x here, that's the set of all n where we selected a bit. So we have 1s under all the blue columns and 0s under the pink columns because we didn't select those columns. So then x within f of x is taking f of x and looking at the bits of x in those columns and collapsing them down. So we've just taken x and we've removed the pink columns and smashed it together to get rid of the gaps. And then we're going to measure the density of that. Okay, so that's the picture of what's going on for church stochasticity. MWC Stochasticity, which stands for von Mises-Wald Church stochasticity. That's the same thing as Church, except our selection functions can be partial now. When we ask if we want to select the nth bit or not, we don't have to say right away. What this sort of corresponds to is instead of saying yes or no to the nth bit, we now give a computer program. We say, here's I, and that's the index of a Turing machine that I want to run. And if it halts and gives me 1, I want to select this bit. If it doesn't halt, or if it doesn't give me 1, then we don't select that bit. So the important thing is, I've now made my choice in giving that program. I can't later go back and feed it information. I can't later go back and modify it. It will just run. But I don't have to wait for it to stop to continue going. So that's slightly more complicated in sort of the concept of what's going on than Church. Formally, it's a very simple modification. Your selection functions are just allowed to be partial. They don't have to be total. But let's see an example of what's going on. So once again, all of our coins are covered by cups. And we start our program, which is what the green circle represents. The program for deciding the first bit has started running, but we don't know what it's going to do yet. Okay, so at the next step, it's still green. So the program still hasn't stopped running. But we started the program, so now we're allowed to look under the first cup, and we see a 1. So we say, okay, we now give a program for the second bit. In this case, we give a program that just immediately says, take it. So that's why it's blue, because the program has just immediately halted and said, take the next bit. So we look at the next stage, and we see that we look under the cup and we have a 0. But the first coin, that program is still running. It hasn't selected or denied that yet. Okay, so now using the information that the bits start out 1, 0, we start the next program. So we have a green circle. And this is a 1. But you know, in theory, we'd want to go back and say, okay, it's a 1. So we hope our program, you know, selects this bit. But unfortunately, we're not allowed to change it. It's just going to run and it's going to do whatever it does. So now we start this program, or the next program for the bit index by 3. Okay, so what happens here? Well, 2 things happen at this stage. We notice that the bit index by 2, our program stopped and it said, yes, we want to accept this bit. So that turned blue because we accepted this bit, but we didn't have any control over it past the point where it became green. The bits for 0 and 3, those programs are still running, but we've selected the 4th coin immediately. So we gave a program that just immediately said, take it. So now we look at the next stage and we see the 0th coin. That program finally terminated and it said, no, we don't want to take this bit. So that turned pink. And we've also fed the information of the first 5 coins into our program, and it said, I don't want to select the next coin. So it said that immediately. That's why we have a pink circle there. And this process just sort of continues all the way out, just like in the MWC stochastic case, or the Church stochastic case. So once again, f of x is all the columns that converged to 1, or converged and said, select this bit. So those are the blue columns. So at in the column indexed by 1, immediately we took that. So that's why that's a 1 for f of x. In the column indexed by 2, we didn't select it immediately, but after looking at the first 4 coins, it halted, but we started it after looking at the first 2 coins. And similarly for the one indexed by 4. For 0 and 5, the program's halted and said, don't take these coins. But for 3, in this column, the program didn't necessarily halt. We haven't seen it halt, and it could have just gone on forever and ever and ever and never made the decision. So by default, if we don't make a decision, we don't accept the coin into our subsequence. So that's why that one isn't blue, because we never accepted anything. And then x with an f of x is just once we have f of x, it's the same principle to create the set that to create our subsequence that we're looking at. Okay? So these are sort of the big famous examples of stochasticity from the literature. And that brings us to sort of our philosophical stance on how we're viewing these things. So stochasticity and density are motivated by intrinsic density. For intrinsic density, we said, here are the things that we're going to measure, and then just make sure that they're all the same. And we don't care what value they are, as long as they're all the same. For stochasticity, that's generally coming from the perspective of randomness, where we say, here's our measure, or here's the R. Here are the ways that we can select things. Now make sure that all of these things evaluate to R. So fundamentally, we're going to use, say, church density to refer to church stochasticity. But when we say church density, the perspective we're looking at is we're studying the class of all of the things that have church stochasticity for some parameter, which is a different class than the set of things which have church stochasticity R for some fixed R. The same sets are going to come up in both of these studies, but the class that we're studying is different and will have different properties. So that's just a minor note. Throughout this, for the rest of the talk, you're just going to see like MWC density, church density, and that's just going to mean stochasticity after a fashion, but the word density is communicating our intention for what we're going to do with these sets. Okay, so now we want to look at our applications from into and within. They worked for asymptotic density, and they worked for intrinsic density. So now let's apply them to church and MWC density. And what we're going to say is that they work pretty much exactly the same way, which is good. But other operations, such as the join, union, those are not going to work nearly as nicely, which is another motivation for why we care about into and within, is because they work over a broad variety of different classes, whereas other operations work differently in those same classes. Once again, you could ask the question, what values of MWC density or church density can you achieve? And once again, just a probability theory argument says, well, they have to have Bernoulli R or mu R measure 1 for the MWC density R sets. So once again, we have the whole unit interval. So we want to study exactly how these sets interact with one another across different densities. Okay, so within an operation, absolutely nothing has changed. Oh, one thing I forgot to mention, everything we're going to say from this point on, we're going to phrase for MWC density, but it's going to be true for church density as well, because if we're going to prove something, we're going to take a selection function, we're going to modify it to prove our result. And if we started with a total selection function, none of our modifications will make it non-total, so everything will work for church density as well. Okay, so within an operation, as I said, nothing changes. So if C is computable and A has MWC density alpha, then A within C has MWC density alpha. So nothing's changed here from the intrinsic density case. With the into operation, it's almost the same. So if A has MWC density alpha relative to B, and B has MWC density beta relative to A, then B into A has MWC density the product. The difference here is that now we need relativization on both sets. But unlike the intrinsic density case, it's open. We don't know if this is tight, if you can eliminate one of these or not. But we know that the example that we gave for intrinsic density to show that this was tight will not work in this case because the join completely fails to work in this setting. Okay, one thing that we can recover is the intersection also multiplies densities, as in the intrinsic density case. But an important note is that for the intrinsic density case, the proof was just a quick corollary of our within lemma and our into theorem. In this case, that proof doesn't go through because of the extra relativization for the into theorem. There's some technical details that you can't verify for the proof for intersection, but fortunately, you can just recover this by proving it directly. So far, into, within an intersection, all good. All of them behave pretty much the same way. But things start to go off the rails with the join. if A doesn't have MWC density 1, then A join A doesn't have MWC density, because whenever you see something in the even, you select the next bit and you know it's going to be there because you have something join itself. So MWC density just completely fails for the join. More worryingly, or perhaps more unexpectedly, disjoint unions don't work either. This is a little bit harder to prove, but there exist disjoint sets A and B such that both of them have MWC density, but their disjoint union does not. So you can look at various ways. How can we address this? How can we fix this? So one thing we can prove, fortunately, is for non-disjoint unions, if you have relativization in both directions, as in our Into theorem, then the union has MWC density alpha plus beta minus alpha beta, which the inclusion-exclusion principle says if this has density at all, it should be that. And one reason why disjointness doesn't really work here is because if you have these assumptions on A and B, then you can apply our theorem about intersection. So if they're disjoint, their intersection has density 0, which implies that one of your starting sets had to have density 0 to begin with. So you can't use disjoint unions to really change density if you have these relativization requirements in place. So if we think back to how we constructed sets of intrinsic density R, we needed unions, we needed disjoint unions to have fine control over how we achieve those densities. So fortunately, we have a special form of disjoint union we can use to recover part of that proof. So if we have A and B with relativization in both directions, then A, disjoint union B into the complement of A, has MWC density alpha plus beta minus alpha beta. So sort of what it should have. This is an immediate corollary of the regular union because B into A complement won't necessarily have MWC density relative to A, but you can prove this. And as a corollary, we can do sort of the finitary version of what we did in the intrinsic density case. So if Q is some finite sum of powers of 2, then every one random computes a set of, sorry, this is a typo, this should say MWC density Q. But it's open if infinite unions work with MWC density. So it's unclear if you can do this for every possible value. Okay, so very quickly to summarize before I'm done. So we took these two non-computable operations once we realized computable operations weren't going to work, and we used them to essentially get every intrinsic density from a random, and possibly if the intrinsic density we want to achieve is non-computable, we might need that too. And then for Church and MWC density, they did pretty much the same thing, although we needed more relativization. And there's some open things for the MWC density case, but those came from the different behavior of sort of traditional operations for sets as opposed to the into and within operations. Okay, so that's everything I have to say.
All right, thank you, Justin. So let's thank him for his talk. However you want to do that. Okay, little clapping icons. Are there any questions? Okay. If there,
I have a question.
Yes.
Maybe not too good one. Is there sort of anything short you can say about how intrinsic density is related to a dimension?
So I don't know specifically, but we do know that, so Astor proved that the the degrees of intrinsic density 0, for example, are higher DNC. And we also know that for arbitrary intrinsic density, they are eventually, in some sense, closed upwards. So it seems probably unbelievable there would be anything too strong you could say that, a fixed intrinsic density has a specific dimension.
Okay.
Also, I have a question about the lemmas relating within an intrinsic density. Can you go back to the slide somewhere in the middle?
Sure.
Yeah. It's probably an easy question, but I just wanted to make sure. Yeah, forward. Yeah, this guy, right. So does it relativize to general C?
Yes.
Like if you just have like the intrinsic density of A relative to C is alpha, right?
Right. So, and we actually use that here. So the relativized form was necessary to prove for the intersection. So yes, in general, it relativizes just fine.
Ah, okay, right. Yeah, I missed that. Thanks.
Mm-hmm.
Okay, if there are no further questions, we should thank Justin again. All right, now I'm a little bit at a loss. I think we do